Thank you and welcome back to Module 4.5. We're still on Module 4. This is Module 4.5, Redox Potentials in Non-Standard Conditions. Remember, we stated the standard conditions: concentration of 1 molar, pH of 0, temperature of 25 degrees C or 298 K, and pressure of 1 atmosphere or 760 millimeter mercury. So when any of these conditions changes, then we no longer have standard reduction potentials. The one we said is E naught values. We will now have reduction potentials in non-standard conditions. We want to find out how we can calculate this. We're going to look at redox potentials in non-standard conditions, look at illustration, we'll look at concentration cells, which I mentioned before. We'll also look at electrodes used to measure pH, and we'll look at the second illustration and we'll conclude. Redox potentials in non-standard conditions. The E naught value of test electrode is measured when concentration is 1 molar, pH 0, temperature, I've said that. So these are the conditions that gives the standard conditions. When the temperature, pH, concentration deviates from the standard conditions, then the redox potential E differs from the standard value E naught. The relation between E and E naught is given by the Nernst equation. So the Nernst equation is represented as equation 1 or equation 2. They are the same, except that if you look at it in the first equation, we have E equal to E naught minus. Second equation, we have E equal to E naught plus. Now, when you have the change in minus plus, if you look at equation 1, we are having reduced form divided by oxidized form. Whereas in equation 2, we're having oxidized form divided by reduced form. Whether you're using equation 1 or equation 2, you will arrive at the same thing. The next equation is useful for finding electropotential at concentrations other than 1.0 mole, that is, under conditions that are non-standard conditions. Also measuring small concentrations of ions. Illustration 1, we are given the E naught value for this reaction. Say what is redox potential at 50 degrees C when the concentrations of Fe3 plus and Fe2 plus are 0.1 mole and 1 mole respectively. Now if you look at this, concentration of this is 0.1 mole. It is no longer molar solution. So we'll go to our equation. If you remember equation 1, E is equal to E naught minus 2.33 ROT and F log reduced form divided by concentration of oxidized form. Now you have to look at this properly and ask yourself question between Fe3 plus and Fe2 plus, which one is the oxidized, which one is the reduced? Of course, if you look at it, the oxidation number of these are higher. 3 plus is higher than 2 plus. So plus 3 is oxidized, plus 2 is the reduced form. So we substitute, we are given the standard E naught as 0.758 volts. We substitute here. 2.303 is there. R, the gas constant, temperature 50 degrees C plus 273. We'll get this 323. Electron transferred is 1 electron, and our Faraday is 96500. Log concentration of reduced form is 1 molar. Concentration of oxidized form is 0.1 molar. We'll work this out and you get 0.694. You see, under non-standard condition, this is different. 0.694 is different from 0.758. Concentration cells. I mentioned this before. Now, when we look at the reduction potentials corresponding to metal ions in two oxidation states, let's say Fe3 plus Fe2 plus and then CO3 plus CO3 are significantly changing or often significant changes in the presence of complexing agents. Now, this is due to the fact that a stronger complex is formed between the ligand and the metal ion in high oxidation states. For instance, E0 value for Fe3 plus and Fe2 plus is equal to 0.76. But when it is in the presence of cyanide ion, now the value will fall because cyanide ion becomes a complexing agent. Therefore, the effective concentration of the desired form is greatly reduced, which can be seen from the next equation to give an E0 value which is less than, E value which is less than E0. Like the last calculation, we had E0 as 0.758, and then when we calculated the E value from the next equation, it was much lower. So we can have concentration cells when we have a cell coupled. For instance, several half reactions involve the presence of hydrogen. Look at the one we used, in our example of balancing redox reactions. So E is equal to E0 minus, we're using the next equation now, our oxidized and reduced form. So this is reduced and this is the oxidized form as the denominator. From the above equation, E depends on concentration of hydrogen ions and hence the pH. If we apply the next equation to standard electrode potential, in which the reduced form is a pure metal, we have equation 3, which is reduced form is a pure metal, oxidized form is a metal ion. If a cell is set up by connecting two electrodes of the same metal, dipping into metal ion solutions of different concentrations, a small potential difference will be set up, and such a cell will produce a small EMF. And we'll call this cell concentration cells. The only difference is the concentration in the two half electrodes. We can have the same electrode of copper or zinc in both electrodes, left-hand side and right-hand side. But once the concentrations are not the same, then there will be a potential difference or a potential gradient between the two cells. And this is as a result of the different concentrations. And we call these concentration cells. Electrodes used to measure pH. We have mentioned this. So if we now look at the potential of the standard hydrogen electrode and apply the next equation, then it means E will be equal to E0 minus 2.303 RT over NF log 1 over hydrogen ion concentration. The one above there is the concentration of the reduced form. That is, we're now assuming the reduced form to be equal to 1. Now, but E0 for hydrogen is 0, and the number of electrons transferred is 1. And of course, we know that 1 over hydrogen ion concentration will give us the pH. That is, log of 1 over hydrogen ion concentration will give us the pH. Therefore, E will be equal to minus 2.303 RT bracket pH over F. Hence, comparison of the potential difference setup between a hydrogen electrode and another electrode whose E value depends on pH forms the basis for an electrode system which can be used to measure the pH of a system. So in practice, we use a hydrogen electrode. This hydrogen electrode is also difficult to use because of the alternating flow of hydrogen gas and other issues. It's not easy for us to carry the cylinder of hydrogen, so we have other electrodes can be used, such as the glass electrode or even the calomel electrode, and this functions as a pH meter. We're looking at another illustration, calculation of EMF of this reaction. It's very simple. We're giving the concentrations, we're giving different E0 values, so we substitute in our next equation and we calculate, solve, and we get our answer. We have looked at reduction potentials in non-standard conditions as the application of the Nernst equation, looked at concentration cells, looked at electrodes used to measure pH, and some illustrations. Thank you very much. As we are waiting to go to the next class, that is the last module in module 4. Thank you and God bless you.